Okay. So can I get you 6 hydrogen protons to stand up for me and tell me about everybody's flashlight work? Okay, very good. Now turn off your flashlights, please. Proton cycle was explained to me in the Navy, explained to me in high school in physics, and Jay Gill and Burns and these guys probably teach it wherever they work. It's extremely complicated, but it's very simple when you do it, when you really think about it. This is going to be a very condensed, not quite scientific version. So these guys are 6 hydrogen, they're 6 protons, okay, which is ionized hydrogen atom. They're floating around in there, the pressure is increasing, they come together, okay, 4 of you come together in the center as close as you can get. And, right. Then these 2 other protons are flying around, and they decide to get in on this here too. Right now we're in this stage where 4 protons are coming together. Okay. Now these other 2 protons join in here. So everybody join together and get real as close as you can. Don't be scared. You're not going to fuse unless you get in there. Okay, very good. Okay, now this is what they call a beryllium atom. Okay, a beryllium, is that right? Okay. Am I right? You tell me if I'm wrong. This is the beryllium atom. The beryllium atom decays almost instantly into 2 helium atoms and then 2 free protons. So 2 protons hit the road, but as you hit the road, turn on your flashlights. You 2 protons. Now you 2 helium atoms split apart and move on over this way for me, and don't turn on your flashlights. Okay, so can we do that one more time, but just quickly? So everybody turn off your flashlights. Alright, now get together, split up, 2 helium atoms, 2 protons, take off and shine your lights.
Back on.
Okay. Wait a minute, helium atom, you're not emitting any light. Okay, thank you. Okay, so that's what happens in the sun. Thank you for your demonstration. You're welcome to keep your flashlights if you like. We have some stray atoms producing light over here too.
Stray gay atoms.
Anyway, that's the proton cycle. Okay. And the light you see from the sun, the light outside that we all enjoy and keep us warm, is generated by just that. The protons that do it are a little bit more similarly sized than our protons, but they create a liquid beryllium state, decays immediately, 2 hydrogen atoms or helium atoms are left over, 2 protons fly out of the process, photons are emitted in this process. Those photons go through, go back here.
Gary, do the CNO.
Pardon me?
Gary to do the CNO.
I need more volunteers for that. He's talking about stars that are larger than the sun, much larger, have a different process, the CNO cycle. This is called the proton cycle. It's a little more complicated than this, but basically that's what happens. These protons are so pressurized and they've been stripped of their electrons, which we call an ionized state. They're so enormously pressurized that the strong and weak nuclear force are irrelevant. They come together, fuse, split apart, emit some of their energy as light. And much brighter than those flashlights. But that's basically what happens. And there's another version of it. So here's Jay Gill, Burns, the rest of the guys. Well, that's probably good. They all come together and form a big beryllium and split up. There's your helium and your 2 protons. All of this reaffirms to me, whenever I think about it, the genius of Albert Einstein, especially as an individual making this kind of discovery with this relativity. You know, right now all your discoveries are made by hundreds of scientists working on projects that are interlinked across the globe. It'd really be nice for astronomy if we had one guy, preferably from our club, come up with something revolutionary. You know? That's proton cycle. These photons are emitted. They go through, remember, the radiative zone, the convective zone. They finally get to the photosphere, and they're shot out, and that's what we see. Now the chromosphere, or the corona, is a whole different story. The corona, for some reason, goes from 10,000 degrees at the chromosphere back up to millions of degrees outside, you know, a whole half a diameter away from the sun. It goes back up to millions of degrees. And there's all kind of theories, but nobody knows. Okay? The Solar Dynamics Observatory was launched, and I'm going to pass this around if you want to have one and then pass it around. It was launched by NASA and your tax dollars a couple of weeks ago. And it's going to have some instruments that are going to be able to study that a little bit more closely. And another caveat, Junior was barking and growling at me the whole time I was in the hallway. He didn't like the sunsuit at all. While we're at it, we'll go ahead and pass these around. These are glasses which are safe for you to take. And if you have some kids or friends that want some, take as many pairs as you want. And you can pass those down. course, we can't use them today, but, now, they say it takes up to 100,000 years for the photon to get out to the photosphere. I would also conjecture in there that it probably takes less than a minute for a lot of the photons to get out too. It's just a random bouncing back and forth, being absorbed, re-emitted, reabsorbed, re-emitted by other atoms as it's on its way out. The sun is almost a perfect sphere because of the mechanical balance between gravity causing collapse and gas pressure causing expansion. So, in layman's terms, stuff's blown up on the inside, stuff's compressing on the outside, it reaches an equilibrium, and it's been there for a long time. It's not quite as much of an equilibrium as we'd like to think, because the surface of the sun, rises and falls by several hundred miles anywhere on the surface. But as far as the total size of the sun, it's basically neutral. So when you have cool gas, you have less collisions. The reason those hydrogen atoms hit each other, like we saw in the demonstration, is because the gas is hot and has a lot more pressure, so they get closer and hit each other. It takes about 25 million degrees to heat those protons up to a point where they'll disobey the laws of physics, and at least the low temperature laws of physics, and combine with each other in nuclear fusion. This is different than on the submarine I was on or the nuclear power stations that are in Georgia. This is a totally different process because those things are splitting off pieces of uranium atoms. It's not fusion, it's fission. The hydrogen, or the atom bomb that dropped on Hiroshima or whatever was fission, it was not fusion. This is much, much more powerful, okay? Well, now we have hydrogen bombs. The sun's core is hotter because of the increased temperature and pressure. It takes 15 million degrees Kelvin to start hydrogen fusion reaction. We just talked about that. The density of the sun is 1/4 that of the average Earth density. Most of the sun is pretty close to the density of water or less. Okay? So that's some other interesting things that you don't really think about. It's not very dense. It's a gas. Until you get to the core, then it's very dense. Every second, the sun emits this number here, which is a really big number of watts. Okay? And that's figured out by E equals mc squared in this equation. And if it were a light bulb, that's how many watts per second come out of the sun. The sun is enormous. I can't stress enough. Who can tell you what we're seeing here? You're seeing the sun. You're seeing the sun is what you're seeing. Just like you're holding a mirror up and seeing me. I mean, yes, it's reflecting off the moon and it's showing you some of the characteristics of the surface of the moon. But what you're seeing here is sunlight. Okay. In fact, if I turn my H-alpha scopes or my sun scopes towards the moon on a full moon, I can see an image of the moon. Because we're not seeing moonlight. Moonlight doesn't exist. Okay, it's sun reflected off the moon. Magnetic fields of the sun. This lecture is not really much about that, but that's what controls the prominences and flares and sunspots and other magnetic activity are the twisting and turning magnetic fields of the sun, which really are, because the sun is not a solid, remember it's a gas and a pretty, let me say non-dense, not very dense gas. As it turns, the different parts of the sun turn at different speeds, cause their magnetic fields to get twisted, twisted, twisted. Finally, they give up. Parts of it fly off, take plasma with it. That's what we see in our telescopes as prominences. Now, some people call them solar flares. In fact, 99% of the people would say that's a solar flare right there. I've been chastised on cloudy night solar form many times for saying solar flare. I should have said prominence. So those are actually called prominences. But if you want to call them solar flares, have it. The solar cycle. 11-year solar cycle. The sun's magnetic field flip-flops every 11 years after it's been twisted so much about this differential rotation of the sun. If I'm talking too fast, I'm sorry, I'm an air traffic controller, you'll have to. The magnetic field becomes more and more twisted, differential rotation. Really the cycle is 22 years long if you think about it. Right now, we're right about here, and right about here is where the Earth's going to end according to Hollywood. And we are in a heightening solar cycle, and I believe this is going to be, sir?
You really think we're out in the middle of it? It's not that spotty, and we have another.
I'm no expert, but I'll tell you this. The last 3 or 4 years that I've been doing this strictly solar observing only, I've seen nothing compared to what I've seen in 2 days of solar observing now. Okay, you could add up everything I've seen up until October of last year, and it wouldn't even come close to a fraction of what I'm seeing every day now. So, you know, like I say, I'm no professional scientist, but it seems to me it's much more active.
Well, it's more active, but it also